So one of the questions I think that comes up a lot is, why what we're doing is different than what other people have done in the past and the different parts of the modality of using bacteria. Do you want to kind of explain really how we've gotten here and the different kinds of approaches that haven't really worked and why we think the decoy platform will be successful?
Sure. So there are a number of companies that have tried bacteria-based approaches. And in fact, we can go back to the 1980s, and that was really when one of the first modern approaches was done. And there are still several companies today that are developing live bacteria approaches. And it's really somewhat different than ours because those approaches are based on trying to target the live bacteria directly to the tumor, trying to modify the bacteria in a way that they might preferentially colonize or preferentially grow in the tumor. And so you don't have the real systemic response. And there are still some companies working on that, and we certainly wish them well and hope they succeed. But we don't have any approved drugs of that type. And I think there are two reasons that we don't yet have approved drugs with live bacteria, and that also will highlight why we chose to work with dead bacteria. So as I mentioned, the live approach tends to try to target the tumor, and we really feel that in order to have a more efficient or improve on existing cancer therapy for advanced tumors or metastatic tumors, we really feel that we need to activate the immune system systemically. So by using killed bacteria, we don't have to worry about causing an infection. And we can have the bacteria go throughout the system to some extent and activate the immune system throughout the body.
Now, are you saying the live attenuated bacteria therapies don't get much of a systemic, and are they in the system longer, or?
So they're in the system probably in most of the system for a very short time, like our product. But those products are really designed to have their greatest effect after they have gotten to the tumor and started growing in the tumor. That's really where they're designed to have their effect, not after being cleared very quickly in other parts of the body.
Got it.
So there's another very significant difference between those approaches and ours. In most of those settings, because the bacteria are live and because they are growing or dividing, proliferating, they have to worry about molecules on the bacteria that might be toxic. And by the bacteria expanding, dividing, they may eventually make too much of a toxic molecule. Now, of course, the most toxic molecule in the bacteria is lipopolysaccharide, LPS, or endotoxin. It's the most potent immune stimulator ever discovered, and it's one of the main sources of septic shock or toxicity when people get a bacterial infection. And that's because there's a lot of this molecule on the surface of the bacteria. And if a bacterium can get into the body and start to grow, as it multiplies exponentially, eventually you have too much of that very toxic compound. And so the companies that have and are still working with live bacteria have completely eliminated that molecule from their product. They've done that genetically. They induce a mutation. The bacteria no longer produce that molecule, the LPS.
Yeah.
And they feel that they have to do that because they can't control how much their bacteria will divide when they're in the body and associated with the tumor. Now, we approach this very, very differently. As you know, our approach in thinking about this originally we thought, well, gee, this molecule, this LPS molecule, is the most potent stimulator of the immune system known. In fact, it's known to activate both the innate immune system and the adaptive immune system, and it's known to be able to mature the dendritic cells that bridge these two pathways and that provide the ability of the tumor to be recognized by the immune system. So instead of eliminating it, our thought was, well, gee, let's not eliminate it. Let's just reduce it. Let's reduce it down to a level where now we can feel confident that we might be able to give this safely, but now get the advantage of this immune stimulation.
So isn't one of the insights, because there were a group of folks who went down the path of just using LPS, lipopolysaccharide, as a therapeutic, and the toxicity, and you could only give such a small amount to get the immune stimulation, versus the other side of the table, which was, we'll eliminate all of it and go down that path. And you kind of have come somewhere where we're giving a little bit, but not that much. That's a fair way to put it?
That is a fair way to put it. And so, yes, you're right. There were groups that tried to do cancer immunotherapy with pure lipopolysaccharide. It can be isolated, purified from bacteria. What they found was they actually got a little bit of anti-tumor activity in a colorectal cancer carcinoma study. But once they got high enough, they just got toxicity. They didn't have enough of a therapeutic index or therapeutic window between the efficacy and the toxicity. And so those efforts were largely abandoned. Now, one other really interesting thing about LPS is that a modified form of LPS, I mean, again, and this highlights that it really is an important immune activator. Turns out that a modified form of LPS is used in a number of vaccines against infectious diseases. So it's a vaccine adjuvant, and it's part of several different vaccines. So we know that it can be a potent inducer of the human immune system. And so by reducing the level on our bacteria as we make them and process them, the idea is that let's leave a little bit because it's such a good activator of the entire immune system. But we also have the notion, and this is really an important part of our discovery and our process, that the immune system is so complicated, it's so complex, and so many parts of it need to be activated that if we only activate one cell or one part of it, it's just not going to be enough to attack an advanced cancer. And so in addition to that LPS, we know there are, maybe about a dozen other different immune activators in the bacteria that can both complement and synergize with the LPS to fully activate the immune system. So one of the problems of leaving all of the LPS on the bacteria is that we could then only inject a very small amount before it would be too toxic, and then we wouldn't be able to give enough of all the other things. So by reducing the level of the LPS by about 90% and leaving the other things as they are, we now can give more of it intravenously, but we now, in doing so, we're able to give more of all those other immune activators. And we think it's really the combination of being able to give a little bit of LPS, but also being able to give all those other activators that we can really do something novel, something original.
Has anyone else ever tried this approach?
I'm not, can't be certain, but I'm not aware that anyone else has ever tried this approach. And I think that there are kind of two reasons why I have maybe that confidence. Is that one, we've really looked around quite a bit, and we don't see any other companies working with killed bacteria. I mean, there may be one, but we're just not aware of companies. As I say, there are several working with live bacteria. But there's really kind of one other indirect reason why we don't think anyone else has ever tried this, and that is our patent estate, our patents. We've been able to obtain quite a number and variety of issued patents, both in the United States and abroad. And those patents are based on using killed bacteria with reduced lipopolysaccharide. And if anyone else had ever done that before, we probably would not have been able to obtain those patents.
Well, thank you very much, Michael.